Our last example for partial fraction decomposition is going to be an example where we combine more than one form, which does happen sometimes. So the example we're going to look at is 6x squared plus 3x minus 2 divided by x plus 1 times x squared plus 3 squared. So this is already factored for us, and most of the time when you see combinations like this, they will be pre-factored. Every now and then, though, you'll have to do the factoring yourself. There's quite a bit more computation for this one involved. So I want to show you how this one fits. It fits form 2 and form 5. And the way it does that is it fits form 2 in the sense that I have this square outside one of my parenthesis sets. And it fits form 5 in that I have a square inside the parenthesis as well, or that this cannot be factored further using whole numbers. So the way that I would set this up is the first parenthesis is going to be set up the same, x plus 1. The second two parentheses is where I really combine 5 and 2. So the second parenthesis set is going to be bx plus c over x squared plus 3, and this one is just to the first power. And then I'm going to combine one more using dx plus e over x squared plus 3 squared. So that's taking into account this additional square. The rest of our setup will be the same. We multiply the denominator to each side, canceling out on the left, with parts of it canceling out on the right. What we obtain when we multiply that denominator through on the right-hand side is this kind of long, complex form. And if we were to use the method in which we've used to solve the previous 5 examples, what we'd find is we wouldn't be able to cancel enough of our variables out to really make it an efficient method for solving this. So because we have so many unknown variables, we're actually going to use a separate method to solve this, in which we are going to FOIL everything out and then combine the like powers of x. And once we have FOILed everything out, it becomes this really long formula, which is probably why you can see I don't often like to use this method, but it is simply the best method to use when I have so many unknown variables. So once I have it all FOILed out, what I'm going to do, I don't do anything to the left-hand side yet, and I don't move it over in any way. I leave it right where it is. I'm going to simplify the right side by combining all the like powers of x. So all the x to the fourths I'm going to bring together, and all the x to the thirds and to x squareds and just x to the power of 1, and then all the ones that aren't even multiplied by x. Once I've combined the like terms, it's become a little bit more simple, but the way I'm actually going to set this up is something I can do. Because of the uniqueness of the powers, I can actually set these equal to their respective powers on the left-hand side. Algebra allows me to do that. Now you might be saying, I don't have an x to the fourth on the left-hand side. That is correct, I don't. So I can represent it as 0x to the fourth plus 0x to the third plus, and now I can set it up for each of their terms. So I'm going to create this big, almost piecewise function where parts of this equation are going to be equivalent to their corresponding exponential powers. So a plus b, which corresponds to this x to the fourth, is going to be equivalent to this coefficient in front of this x to the fourth, which is just 0. b plus c equals 0. Then I have 6a plus 3b plus c plus d equaling 6. Then I have 3b plus 3c plus d plus e equaling 3. Then the last one I have is 9a plus 3c plus e equaling -2. Now I can use systems of equations to solve for this and figure out a, b, c, d, and e. So from this I can see that a equals -b, b equals -c, so I can say a equals c. From the last equation, because I know a equals c, I can say I have 9. Instead of writing a, I'm going to write c plus 3c plus e equals -2. So e equals -2 minus 12c. I have 3. B, instead of writing b, I can write, since b equals -c, write -c plus 3c plus d plus, instead of writing e, I'm going to write what I just found e is equal to. So plus e becomes -2 minus 12c, and that equals 3, using this fourth one here. This simplifies to d equals 5 plus 12c. Now I'm going to use this third one here, plugging in what I've already found for some of the expressions. So I'm going to write 6, instead of writing a, I'm going to write c, because it equals, because a equals c, plus 3b, instead of writing b, I'm going to write -c, plus c, plus, instead of writing d, I'm going to write 5 plus 12c. And that is all equal to 6. So by using systems of equations, what I've done is I've manipulated them, and it took a few tries, but I've finally gotten one unknown and one equation. So now I can solve for c. We find that c equals 1 over 16. Remember, c equals a, so a also equals 1 over 16, and c equals -b, so b equals -1 over 16. Since d equals 5 plus 12c, then I can say this is 80 over 16 plus 12 over 16, and I get 92 over 16, or 23 over 4. And since I know e equals -2 minus 12c, I know that it is -32 over 16 minus 12 over 16, which equals -11 over 4. And I found all of my unknown values now. My final expression, I get something that looks kind of ugly and complicated, so I actually want to simplify this and get rid of the fractions in the numerator. I'm left with 1 over 16 times x plus 1 minus x minus 1 over 16 times x squared plus 3 plus 23x minus 11 over 4 times x squared plus 3 squared. And this is the solution for an example of a partially decomposed fraction that combines more than one form.